Good morning, ladies and gentlemen, wherever you are in this world. Nowadays, with Zoom meetings, you basically covered all corners of the world. So usually you say good morning, good afternoon, and good evening. This is the second forum of the Quantum Forum regarding quantum computing. The genesis of this particular forum came with a single question that was raised by Professor Wei Zhao, who is with us today. The question was really very sort of obvious and yet intriguing. The question was, is it necessary to know quantum mechanics in order to do quantum computing? Well, since Olivier is from France, I sometimes use the example that if you want to do French research, French literature research, it's probably important to know French. The same as if you want to do quantum computing, maybe it's necessary to know some quantum mechanics. Well, the question seems to be non-trivial. We started one such forum already. Lots of different perspectives were given by experts. Interestingly, their perspectives were not converging. They have different ideas and different thoughts about the answer to this very simple question. So Jim and I started to think that we should make this, since this is the year of the quantum, this is a possibility of making this a quantum forum specifically for quantum computing. And so we thought of inviting two experts in this area. Wei Zhao, well, the first one were all physicists. So we thought this time we will try to make sure that we at least get some computer scientists involved. I couldn't think of anyone better than my former boss, Wei Zhao from Macau University, who is a computer scientist all in all, even though he was tainted as an undergraduate by being a physics major. But that tainting didn't hurt him from becoming a world-class computer scientist. And of course, Ching Rei was so kind to invite us, Olivia, here today. And I read his bio. He also had some undergraduate training in physics, but also went on to become a very, very well-known computer scientist or as person in that area. So we would like very much to invite them today to first make a short presentation of what they thought would be a possible answer to this question. And I will start with Wei first. Wei, the screen is yours.
Thank you. So let me start to share my screen. And again, thank Professor Feng and thank all of you offer me this opportunity. I really cannot claim myself is a specialist on quantum computing, because certainly when I was a graduate student, there's no such thing. So I kind of self-learned. Actually, I'd like to thank Professor Feng, because my quantum computing started with when we were in Macau, and he invited few physical scientists to talk about that. I guess you remember that. Then make me interested, and I kind of read some books and papers. Let me go down. Why this is not moving? Interesting. All right. my talk actually, this talk was prepared somewhere else, so it's relatively long. So I will rush a little bit because most of you actually know this already. First of all, let's define what computing. Computing, we mean tooling computing. And for some of you, if you know nothing about the so-called tooling, machine tooling computing, basically, let's just define the two following characteristics. One is information digitized, right? You can call it bits or digits, whatever that is. That means the information presented by discrete states. And also computing means you're using finite step and very deterministic transformation step by step to change the information, input information into a final state. That's called computing results. Now, from engineering point of view or from user point of view, normally when you use a computer, classical or quantum, doesn't matter. You have to go 3 steps. Number one, you have to write a program, what we call design program. Second, you need to ask a system to manage the program for you. Especially, they have to allocate a resource to you. Then you can use a computer. Finally, you run the computer and get your results. Actually, it turned out, although we know those 3 things every day, and it turned out this make the quantum computing different from classical computing. I'll be back these slides later. So very quick review what a classical computing. Remember, information digitized, presented by discrete states. In classical computing, we only have 2 states, 0 and 1. And then so-called computing or so-called why can we transfer input information into output? We're using something called logical circuits, right? And called AND gates, OR gates, or NOT gates. And because of time, I'm not going through this example here. When I really tell people, never in computer science, I had to go through the example. This example, say binary adder. You add 2 binary bits and you get the output. So you can design using so-called truth table and Boolean algebra. Eventually you get a circuit. And when you have A, B show up as input bits, and then in SC, you have results, okay? That's by computing by logical circuits. The trouble is, for different computing jobs, you actually need different circuits. So that's not efficient, not economical. A green man, in my mind, this man, I was in the last 500 years, this is one of the few green men we need to really admire and thank, called von Neumann. And he came up with something called machine, which we now call the CPU. I'm not going through the structure of CPU here. Basically, the machine itself will do instruction-based computing. Basically, you say, well, let x equals y plus 1, that will do the one for you. Then if x less than 1, let z equals 5, for example. So they have instructions, they do this one by one. I assume most of you are actually familiar with this. We don't have to go through detail here. So, quick summary. For classical computing, we have 2 ways physically to realize it. One goes through logical circuits, another goes through von Neumann machine. However, if you look how they use in application, then the logical circuits will be ad hoc. For different computing, you need different circuits. Von Neumann machine, general purpose. One machine can do all different kind of computing. So that's very, very powerful. Now, when you have the machine, actually the machine is made by EE guys, or actually so far we're using semiconductor, really the contribution made by people in physics. And the computer science people normally worry about the design program to run the program. So computer science, so I need to really give you a very quick tutorial on what a computer science really is. Computer science really build on top two foundations. One is the theory of mathematical logic, another technology of semiconductor. None of this were invented by computer scientists. So why computer science can be called a science? Because we invent something called a complexity theory. Basically, we can measure how good or how bad a program is by using this theory. So let me give you that through this theory, we can classify computing problems into easy one and hard one, okay? I'm not going on technical too much details, so let me tell you what do we mean easy one. Easy one means the computation time will not grow exponentially as input size grows. For example, when you look at addition, when you add two numbers together, you have n bits. Think about it. You add the single digit bit once, then you go to the tenth digits another time. Basically, if you add n bits, the time taken for you to do it is linear of n. That will not go, as n grow bigger, the time taken will not grow exponentially rather than polynomial in linear array. Unfortunately, not all the problems be that kind of efficiently can be computed. For example, we have integer factorization problem, or you have finding optimal rod in a graph. All those problems, although may not be formally proved, very unfortunately, their computation time grow exponentially as n getting bigger. For example, you can certainly factor three-digit number very quickly, but when the digit go on very big, say 100 digits, the time is exponential of n, so that's troublesome. So computer scientists figure out this theory and classify the problem into easy problems and hard problems. Honestly, most problems we met every day actually easy problem. And of course, there are some very interesting hard problems we want to solve. For example, if you really want to decode a code message, that's equivalent to integer factorization, and you cannot decode it too fast. That's why the encryption works. So this is a quick introduction on in classical computing, the complexity theory. So bad news is we do have some hard problems. The computation time grew up exponentially. That means very, very high. So what are we going to do for this? Because when n is very big and you cannot compute very efficiently. So what we need is looking for new methods that can solve so-called those hard problems quickly. Here means we had abandoned semiconductor-based computation and use other physical means to obtain results. Actually, this talk really intended for computer science senior. You may not believe, say, you can do that. Actually, let me give you a very trivial example. For example, looking for foreign transform, okay? That's the kind of integration process, normally very time consuming. However, if you look in this glass, certainly when you put the one stream light in and when you have a color light out, you did the Fourier transform. The time taken literally zero. So this tells us if we use other physical means, we could significantly reduce computation time. This is where the quantum computing came from. And certainly we have every reason to believe quantum computing is one of those new methods which we use to solving those hard problems. So having said that, let me quickly give you a little bit of overview of what a quantum computing is. In comparison with classical computing, we states have a 0, 1, and here we all have in quantum computing, we don't call the bits, we call qubits. And qubits also have two states. You call the bracket 0 and bracket 1. The difference from the traditional classical computing is those two states can be a superposition. Right? That means this particular state is probability distributed with alpha and beta. And only when you knock down the bit, you know what the state is, and normally you cannot figure it out. So therefore, we can express a qubit by vector. Basically, it's alpha and beta that more or less quantitatively represents the probability that particular bit will be in which state. So that's introducing bit. Then we can have a single bit gate. That's a computing. If the input is Q, output will be Q prime. And input Q will have a two parameter A and B that presents probability of two states, and output will be A prime, B prime. Very interesting is we have the Sank for people working physics. The output can be expressed as a matrix multiplied to the input state. And this matrix M, you have elements Mij. All of those numbers in the matrix are complex numbers. That means for any single qubit gate, if you give me M11, M12, M21, M22, people in physics will make a device and do the computation for you. So far, so good. And I'll skip the number here. Then you have a 2 qubit. The input will be Q1, Q2, output will be Q1 prime, Q2 prime. And graphically, we used to use this two blue star with a line in the middle to present the gate. Now, because we have two input gates, input bits, therefore, each of them can be in state 0 or 1. Therefore, we actually have four states, 0, 0, 0, 1, 1, 0, 1, 1, 1. And the output, again, will be, again, by multiply a complex matrix to the input state, and you can get the output state. If you follow me so far, I think the audience probably have a computer scientist here. They never see this kind of thing. If you can follow me so far, then we're done. I'm now very quickly to bring my conclusion out. So what we're saying is, for logical gates, and in classical computing, we're using truth table to describe. Here, we have a complex matrix can define a logic, can define a quantum logical gates. And here example called C0. Again, I'm not go through example because C0 will be used widely. So it's a blue star with another circle with a cross and a line in the middle, right? I'm not going to introduce a specific function here, it doesn't matter. So now we have a quantum circuit. Basically, if you want to do a computing, you can using circuits step by step. Remember, it's information discrete. So Q1 coming with a single gate, and then Q1, Q2 perform C0, then Q3, Q4 perform another C0, then Q2 perform another single gate, etc. This is computing done. So in summary, this is my very quick introduction to you on quantum computing. A single qubit gates and the CNOTs are complete, right? This we don't have time to prove this. That means for any computation function, just using single qubit and CNOT, you can do anything. Just like in classical computing, use and or not can do everything. Here, only two kind of gates will be sufficient. However, as I show you, a quantum circuit will be a sequence of quantum gates, and those gates will perform operations on the input bits. Now, I have not told you the program yet. Actually, for now, the quantum circuit and quantum program, same thing. That means the quantum program, as of today, is not instruction-based rather than the complex matrix-based. Okay? So, any quantum computing process will be a sequence of complex matrix multiplication performed input qubits. Sounds terribly simple, right? Also, look like this is very symmetric versus classical computing, just a quantum gates replacing the traditional logical gates. So, however, why we need quantum computer is because we believe quantum computing will significantly reduce runtime complexity for hard problems. Actually, this cannot be really proved. At least we have some examples. So for this quantum computer, I would skip this. Quantum computer basically is the matrix of quantum bits, and the adjunct nodes were 2 bits C0, right? So you may not believe, say, well, can you really do fast? Fortunately, a professor in MIT in 1995, he proposed, basically he designed a quantum algorithm to factor any integer in polynomial time. It's a very interesting program. He will first convert the problem into a Fourier transform problem. I think this guy is genius. And he knows the number series so well to transform factorization problem into a Fourier transform problem. And he realized Fourier transform by quantum computing and convert spectral information back to a factor of integer, and then use that to test if the integer is really the factor. So he proved that this can be done in polynomial time. So that's great success. Actually, when that happened, really the whole community is wow. But unfortunately, we cannot prove every hard problem will have that effect. But so this is people believe that's true. In a normal textbook, in quantum computing, normally people stop right here, right? You have a computer, you do it. The trouble is, as I mentioned to you, when you run a quantum computing problem, you are not only just use the resource at the runtime, you actually have a design, you actually manage it. Normally, we believe the overhead use a computer solve problem is the runtime overhead plus design time overhead. However, design time overhead is one time. So when you use the program many times, that means when the n is number of usage, when n very big, you can ignore the design time overhead. That's why we focus on runtime overhead. The question is if this is always true. Now let's look back. Will both computing classical quantum in design time be equivalent or easy? As I told you, in classical computing, it is really easy because we have a Boolean algebra and a truth table to help us to design the logical circuits. In von Neumann machine, we have a high-level language compiler. You literally can write English instruction. Tell computer, say, if x bigger than 1, let z equals 2. If tomorrow raining, push a button to start a pump, those kind of things. So it's really easy. However, now in quantum computing, what do you have? All we have now today is we know the program is made up by complex matrix multiplications. So for any computing problem, you actually have to think and discover that sequence of matrices which multiply together will do the job. Nobody proved that. However, our claim is not easy to think a problem solving be a sequence of complex matrix multiplication, because this is not the nature. To think solve a problem by a sequence of instructions, that's really nature. That actually make my first claim here in the program design. We need to introduce another complexity. The program design complexity, which measures the overhead of design, seems to be potentially very high, very hard. Actually, if you let a CS student say, all right, here I have a problem, say machine learning problem, or that problem, this problem, and you design quantum computing to solve it, the guy need to figure out this matrix multiplication, and that was not easy. Another thing I will not cover here, but I will mention is the management overhead. First of all, for circuits, you don't need to manage because whole circuit is yours. In Voronoi machine, we actually have something called I/O, which is interruption and virtualization. Use these tools, we actually could very efficiently manage the resource allocation for programs. That's what a so-called operating system is for. This part in quantum computing is completely open because we do not have management tools like interrupt or virtualization for quantum computing yet. So we do not know what the management complexity is. So again, back to my very first slides, to use a computer, you go 3 steps: design, manage, and run programs. And our claim, the quantum computing's potential cannot be realized unless we can fully address design complexity, management complexity. That means we need somehow to understand which problem will have a lower design complexity for quantum computing than you can design. If design complexity is too high, you actually cannot do it. Then even computers there, even problem there, you just cannot do it. So this view actually expand computer science at large. Typically in computer science, people only look physical realization and so-called runtime complexity. However, if you include the quantum computing into the part of computer science, then you actually have 3 complexities to worry: runtime complexity, design complexity, and resource allocation management complexity. So I hope I did not run over my time, and this is my brief introduction about my view on quantum computing and what the challenge we're facing. I guess I should stop my share, and so the next speaker can use the screen. I'm done.
Before we go to Olivia, I have a question, which I hope Wei will answer in a squeeze time, because I think it may be a long question, a long answer. You start very much by saying that a quantum state is zero, linear combination of state 0 and state 1. That's a quantum. First of all, the bracket you use is called, in quantum mechanics, called the Dirac bracket, Bras and Katz, and you probably know that. And it tells you that you can since alpha and beta are basically the Fourier expansion of 2 states. It can be anything. So I have heard a long time ago that quantum mechanics, an ordinary computer is 0 and 1, the 2-bit concept. Quantum computing is from 0 to 1. In other words, anything in between, which makes it very complex. Is this a too simple comment to the quantum computing?
My understanding is not from 0 to 1. It is quite random, either 0 or 1, with the probability of alpha square and beta square. That means the state, actually, you just don't know unless you really knock down the bit. So it's not from 0 to 1. It's not a continuous, say, 0.5. There's no 0.5 state. The little particle either 0 or 1, but you never can get it unless you knock down the guy. Then from probability, you can see with alpha square probability is 0, with beta square probability is 1.
Okay. Jim?
So it's a so-called super position, right?
Yeah. Jim?
Thank you. And Wei Zhao, thank you for that wonderful introduction. I actually would like to get a copy of your slide deck if you're willing to share it. My question comes because, I have taught quantum mechanics for years. And, when you look at quantum computing from the point of view of a physicist, it looks a lot like Stern-Gerlach, a succession of Stern-Gerlach machines. And one of the problems that we know when we teach our students about Stern-Gerlach machines is the alignment of the machine as you go from successive phases is extraordinarily important. And so does this alignment problem show up in the engineering of quantum computing?
I need to think about it. What I try to say, first of all, I think your problem points to the, I call the management complexity. Basically, how can you map a program into the resource, which is the quantum bits and the relevant gates, so the computing can be done efficiently. This von Neumann is really too smart. He's not only built a machine to compute, he also designed a mechanism so let you use the computer very, very efficiently. I mentioned, but this is really go on computer science, the operating system. Oliver probably taught about those courses. No, if you don't have interrupts, and the classical computer cannot be efficient. If you don't have a so-called virtualization scheme, you cannot do that. Then at least I myself found, first of all, there are very few so-called quantum computing system guys there because quantum computer just been built, the system people not show up yet. And in quantum computer today, I cannot find those mechanisms help me to manage the quantum computer. And this is maybe should have another talk. But I show you the matrix. This is actually the IBM produced that machine a few years ago. That's all you have. Think about, let me give you an example. Think about your cell phone, okay? Your cell phone today actually runs at least, I would say maybe hundreds of programs at the same time. There's only one CPU here. And how could you have 100 programs run simultaneously? You can typing on the Wei chart, listen to the music, and maybe take a photo. Literally, you can do all time because this virtualization and interrupt help. And for quantum computers, that cannot be done. At least cannot be done today. So that's another thing we're missing. This is like, I would like to say, quantum computer today, assuming the engine is terribly good, then you don't have a wheel, you don't have a tie. So again, to be really useful, you need all the steering tail and the tie and brake. You need all that kind of thing too. That's another. Oliver is claim you're computer engineering, so you know what I'm talking about. Right. So I'm really looking for a practical point of view, how to make a quantum computer practically useful.
Okay, why don't we begin with Olivier's talk? I think we have also someone, one of our guests called Erwin Holman, who has a very interesting question, but I'll wait until after Olivier finish his presentation.
Okay, so thank you for inviting me. I'll try to respond more or less directly to the question. I'm a computer, I became a computer scientist recently, only in the last 6 to 7 years, but before I was a classical, um, I would say classical engineer in the classical world of computing. So I learned that on the fly, and I found out that to better understand what you can do with a quantum computer, you really need to understand a little bit of quantum physics and to an amazing level. So to respond to the question, I say yes, definitively. I hope you can see my slides. Is that okay? Yep. And I would say yes, and even more. I mean, you need to understand physics even beyond quantum physics. You need to understand electromagnetism, of course, quantum physics, sometimes quantum matter. At some point, you need to be interested in thermodynamics, fluid mechanics, some photonics, if you use photonic-based quantum systems. And I would say one of the most important fields in quantum physics is quantum chemistry. One of the reasons is when you look at the biggest potential of quantum computers, it looks like it's aimed at simulating quantum chemistry. And we used to say develop new drugs or new chemical processes and so on. So there's an a huge interaction between the computing you can do with a quantum computer and quantum chemistry. Of course, you need to learn mathematics. And I would say that you need to relearn mathematics because most of the people who do day-to-day computing and develop programs for, developing a new website or even some AI, they use pre-existing stuff that sometimes they don't need to learn in details. So you need to relearn linear algebra. And I would say on top of that, that you need to learn a little bit about probabilities because everything dealing with entanglement, Bell state tests and stuff like that is based on probabilities. So you need to relearn a little bit of that. But on top of that, if you want to understand how the quantum computer works, you need to learn a little bit about engineering, particularly electronics engineering. If you're curious, you need to look at cryogenics as well. And then, of course, you need to come back at some point on some of the deep roots that were presented just before on information theory, how do you design an algorithm, theories of complexity. I was amazed because before I was working in the quantum computing field, I was in AI. And I was surprised that in the AI world, there were very few discussions about the theories of complexity. And then it came out when I discovered the quantum computing world, because you have these exponential speedups or polynomial speedups and quadratic speedups. You need to understand that very well when it's not that much discussed in classical computing. So yes, yes, and yes. And so in the rest of my presentation, I will show you a couple examples of where in my courses that I do on a daily basis, I find this kind of crossover between classical computing and quantum physics. I'm coming back on the previous explanation. When you start to explain what's a qubit, you have this alpha modulo square plus beta modulo square equals 1. Where is it coming from? It's coming from Born normalization constraint. It comes from quantum physics. When you show that you have a Bloch sphere explaining what's a qubit, it comes from the fact that the qubit are a way to explain that the quantum objects that you're handling are both particles and waves. And the wave explanation of what a quantum object is the best way to explain what a qubit is, because you have this amplitude and phase. And then you play with phase. And I would say that when you do quantum computing, it's a bit like if you were doing analog electronics. QFT, Fourier transform is signal analysis. Wave handling with the phase is the equivalent of analog electronics. Everything you do, mostly in quantum computing, is based on that. But at some point, if you have a minimum of curiosity, you want to know what's the physical substrate of those qubits. So you need to know that it's a two-level controllable quantum object. You need to understand that it may be an atom, it may be a spin from an electron, it may be some photonic properties. It may be even more complicated when you deal with a superconducting qubit, which is probably one of the most complicated quantum object to manipulate in a quantum computer. Then, if you look at the key differences between classical computing and quantum computing, Of course, you need to relearn linear algebra. That's what I said. But you need to understand stuff like, okay, you can't copy data. I mean, it's weird. I mean, if you look at the von Neumann model, okay, you can copy data in and out from registers, active memory, then you've got your storage, and you copy stuff back and forth into all these memory layers. In quantum computing, you can't do that. You can only transfer data, or you can untangle data. So it's linked to quantum physics. Then you have to understand everything about measurement, because when you do all your computing with all your qubits, at the end you measure stuff and you get a probabilistic result. And you need to understand why it's random, and why at some point when you do multiple circuit shots and executions, and you can generate a deterministic outcome of that. And this is based on quantum physics. Another example, which is even more complicated, is there are multiple quantum computing paradigms around. Everything we discussed until now was based on gate-based computing, but you've got analog computing from companies like QERA in Harvard or Pascal in France, and you've got quantum annealing, which is yet another model coming from D-Wave in Canada. So, and all the differences between those models are based on quantum physics, because analog systems are really as close as possible to a quantum system that's made to solve another quantum problem, even though people are using it for, solving optimization and decision problems. A couple other examples. When you want to show the difference between a set of qubits compared to a set of classical bits, everything is upside down. You see these things. So you can't copy data, you can't evaluate that, you can't individually erase the data. You change the data, you change the data of the surrounding data. And when you read stuff, it's probabilistic. So this is a mix of mathematics, computer science, but this is explained by quantum physics. So if you don't provide the explanation, I think you miss something, both as a student and as a professional. Another example, let's say you want to know what's in the box, the black box of the IBM computer. You need to understand, stuff that ranges from electronics, because all the qubits are controlled by electronics. Then you've got some fluid mechanics with the helium cooling the system. Then you want to understand what's the cable, what's the electronics, how is the quantum computer looking like? What's its price, what's its weight, what's its power consumption? These are very important things, I think, because nobody cares about it right now for classical computing, even though for LLMs, it starts to be worrying to have these huge data centers. But you need to understand the whole stuff. Another, I would say, funny example is that graph. You may know that. If you want to understand how some varieties of qubit work, you really need to know about quantum physics. So this is a diagram that shows how NV centers work. So it's a specific breed of qubit that's being used in some by some companies. Another example is, if you want to understand what a quantum computer can actually do today and will do in the future, you need to understand, like John Martinis was saying last time in the first episode, you need to understand what's noise, where is it coming from, how you correct it. And this is kind of complicated. So first you need to understand when the noise happens, and it happens every time. What's really strange compared to classical computing is even a quantum computer that does nothing generates errors. So a so-called idle qubit is generating errors. Then you want to understand how the noise is affecting the data. And then you come back to physics concepts, because dephasing, depolarizing, coherent noise, these are quantum physics concepts that are being applied to the qubits that you're handling as a computer scientist. And then you may be curious and you want to know, where is the noise coming from? Maybe you can get rid of that, say, okay, that's a problem for physicists, but it's interesting to know where it comes from. And interestingly, it doesn't come only from so-called decoherence. I would say a mystery in quantum physics, but it also comes from control electronics. Electronic devices which are controlling the qubits themselves are creating noise. And so it's interesting to know the sources of those various set of noise. Then we jump into the era of so-called fault-tolerant quantum computing. That's the dream. That's what companies want to build in the future. So building those so-called logical qubits, which are based on physical qubits. But okay, what's the size of this machine? How many logical qubit do you need in your program? How many physical qubits do you need? What's going to be the overhead of that system? And in the end, it's a complicated domain, which is mixing a lot of things. This is a graph I've been creating to explain how do you evaluate the number of physical qubits you need in a quantum computer based on a fault-tolerant system, and what's going to be the computing time of your program. And if you look at all those 4 dimensions, you have 4 domains. One is computer science, learning about the complexity of your code, how do you speed up stuff. Then you've got mathematics, because error correction is mostly based on mathematics. Then you need to understand why the qubits are not good and how you can improve them. That's basically quantum physics. And in the end, you need to improve the connectivity between the qubits, and that's more electronics engineering and semiconductor manufacturing in some cases. So it shows that you nearly always have a multi-dimensional set of science to at least grasp, maybe not be expert on, but at least grasp to understand all the details and all the connections between those different fields to know when we will have a viable computer to do all of that. Another example, which is mostly about crossing quantum computing and classical computing, but not quantum physics, I would admit, is understanding where are the fixed and variable costs. So if you look at the John von Neumann model, the data is dynamic. So you've got classical compiled code. It's using dynamic data and some kind of also dynamic libraries, which are added to the compiled code, and then it outputs data. But if you look at a quantum code, the code contains the data. And you should ask why. I mean, if you're a curious person in classical computing science, you need to understand why. Why the code is containing the data. And so it means that every time you have a new data in your quantum code, you need to recompile the code. In most of the cases, there may be some ways to avoid that, like using an oracle function, but it's not easy. And then you've got a connection between both worlds. So the classical world is feeding the computer with code that contains the data. And so this is connected to the whole stuff we discussed before. Another example where you have a connection between, I would say, computing science, both classical and quantum, and physics. When you look at the traditional way to explain that you can obtain a speed up with a quantum algorithm, so whether it's an exponential or polynomial speed up, you have this kind of curve. I did this curve. I reused this curve from many different sources. But it happens that this curve is misleading. The right curve should be that one, using a log scale for the computing time. And if you take the example of the famous Grover algorithm that is supposed to help you solve search problems, and which has only a quadratic speed up, it happens that you can have an improvement between a classical way to solve a decision problem and the quantum version only after thousands of years. Okay, I would say that's just math. But what is the reason? The reason is we have very slow gates in quantum computers, and the slow gates are linked to quantum physics. So if you want to improve that situation, you need to understand how do you improve the speed of the gates. And there are some limitations to understand depending on the kinds of qubit you're using. Another example, and that's going to be the conclusion of my talk, is when you do quantum chemistry, you need to understand Schrödinger's equation, and you need to understand, with a mix of quantum physics and mathematics, what are the ways to solve this equation. So the history of quantum physics says you can split the equation, you have a variable separation between time and space, and that's the way we solve the equation, particularly for hydrogen and so on. But then you have a lot of mathematics being involved, the Fourier decomposition, you have various numerical methods that are being used right now, the Hartree fork, post-Hartree fork, GFT, and stuff like that. And then you have quantum computing, which is the new, I would say, the new kid in town that can help you solve this equation and do quantum physics with a quantum computer. So this is showing that the interconnection between those different fields is amazing. And one of the reasons why I'm passionate about this field, even though it's very difficult and maybe we'll have to wait for more than 10 years to have a functional fault-tolerant quantum computer, is we have the best concentration of science in that field that I've ever seen in my life. That's why I love that field. And another thing is tomorrow, I'm starting a course in a school in France explaining classical computing to quantum scientists, the other way around. So creating bridges between those two worlds.
Huh. Interesting.
If you are interested by this, I've got a book. So my book is over there. It's a free book, so I don't sell anything. It's open source. You can download it. It's on archive. It's on my blog. It's a very large book, 1,500 pages, which is looking like my presentation because it shows the history of quantum physics. It explains also where we are with classical computing, and it shows the bridges between those two fields. And it covers everything. I mean, quantum computing, hardware, software, use cases, even telecoms and sensing and stuff like that.
Excellent.
Thank you, guys.
Thank you. Thank you so much. We have a question from one of the attendees. I think his name is Holman, Holman.
Hi, can you
Erwin
hear me?
Holman. Yes. Would you like to ask the question and show also, you can show your face if you like.
Yeah, can I switch on the
Tell me,
camera?
say a little bit who you are.
Yeah, I'm Erwin Holman. I'm a computer science graduate so I have a master in computer science long time ago. I've developed an interest in quantum computing, also practical applications like annealing and stuff. And I'm doing a lot of knowledge development for myself on this area by visiting events like today's, but also doing courses.
Okay. Well, what is your question?
My question is, it was the first presentation. Of course, it is a bit complicated to get something done by a quantum computer, but I noticed there is a strong similarity with what we saw maybe 1950s with classical computers, where they basically had to hardwire a tube valve computer with a sort of a switchboard to get it do something. So I see a lot of similarities between that and what we now have in classical computing. So the absence of proper high level tools for compilation and coding is, I think, a temporary problem. It might take a few years. But we're really working on very small devices on for quantum computing, and we don't have proper tools because the equipment is not scalable enough at this moment. That is so. I think the statement, we don't have high level compilers, interpreters, and development tools. True, but I think it's a temporary situation. And look at the history of the classical computer. So my question is, do we agree with that, or are there more fundamental problems to challenge, to fix?
This question is to Wei Zhao.
Yeah, yes, please.
Okay.
I agree with what you say the first half. That means at this moment, quantum computer normally just a bunch of hardware, and we need a lot of surrounding mechanism to support make a computer better. Certainly, quantum computer, us people in physics working on, will be smaller, better, low cost, low energy consumption, etc., etc. That I totally believe, agree with you. Now the question is, how can we came out? Basically, the classical computer in, let me just repeat what Holman was saying. What he say is, classical computer in the 1950s, people invent something called a high-level language. Then people invent compiler, which translate high-level language down to machine instructions and beautifully, and that was done. Which is true. Now, so we can then certainly expect somebody going to invent high-level language for quantum computing, or just use the C++, just invent another compiler or basic translator to translate high-level C++ language program into quantum computer machine executable. Will this happen or not? Let's look what happened for classical computer in 1950s. The reason we are able to do the translation, and translation was done successfully, correctly, and efficiently, is because we hold something theory called formal language, which can precisely define what a program is and will tell us how to translate mechanically step by step. So this was done by a course compiler in computer science. So formal language was the tool to make the translation happen. And formal language actually is a theory. Actually, the formal language was not created by computer scientists, but again, was created by MIT professor in linguistics. At this moment, I have not seen, let's call it quantum formal language being invented yet. If we don't have the tool, then the translation will be ad hoc, time-consuming, and maybe with errors. That's the problem. So again, I'm not closing the door, say it will not happen, but unless you have that theory, like a formal quantum language theory came out, tell us how to do the translation. Otherwise, we have trouble.
Yep.
That's my view.
Thanks very much.
Olivia?
Can respond as well if you want. Yeah, I agree with Zhao, but I can add some stuff on the practical aspect of that. One is the language of programming quantum computing is based on linear algebra. So either you learn linear algebra or you don't use it. So it's kind of 1 and 0, I would say. But still, we could have potentially higher levels of abstraction in the tools which are provided. Actually, it's already happening. Let's say you're using Qiskit from IBM online or using a tool from Classic. It's an Israeli company which does a compiler. There are ways to use, I would say, higher level objects. And when you look at the way people program those systems, most of the time they use existing templates like the QFT, so the Fourier transform. They use the period finding stuff. They use a data preparation stuff. I would say most of the way you use regular algorithms is templatized. And it happens that a lot of the work when you're programming a quantum computer is preparing the data classically. So you have a lot of classical work before you use your quantum computer. So let's say you do quantum chemistry, for example. You need to have a classical computing of your many-body system that's using a classical software tool, which is preparing the code that you feed into your quantum computer. So there are many ways to simplify that because it's very costly to prepare the stuff you feed into your computer. Another example, if let's say you're an engineer in aerodynamics, I mean, in the space industry or in the aerospace industry, you want to do computational fluid dynamics and computing. You need to turn a non-linear problem into a linear problem. So again, you have some classical work to do before you program your computer. And the last example is the one I did in my presentation. It's analog quantum computing. In an analog quantum computer, you don't have a series of instructions that you feed into your system, like with the von Neumann model or the gate-based quantum computing model. What you do is you reformulate a problem into a different way to formulate a problem, which is usually a kind of graph. And the quantum computer is solving this graph, the problem formulated in the graph. So again, it's a dealing with classical tools which are converting a problem into another problem. So there are many different concepts, but I'd say the classical computing understanding is very important to be able to drive a quantum computer.
Okay, thank you.
You know, the way I look at a computer now, I mean, I go to a computer, I want to solve a problem. I learn a language, whatever computer language there is at the moment. I write the program, and hopefully I solve the problem. We haven't reached that stage in quantum computing yet. Am I right?
Well, you program with many languages, I would say. But it's the same. Let's say you're a web developer. If you're a web developer, you won't use one language. You will use PHP, JavaScript,
Yeah, of course.
other languages. So quantum computing is about the same. You will have classical tool that you use to prepare your data. You will probably use Python or sometimes C++ with, let's say, a quantum library to drive your quantum system. You may develop a separate tooling to exploit the data that comes out of the system. And another example which shows the hybridization of the way people are using quantum computers is the role of machine learning. Machine learning is all over the place. I mean, not quantum machine learning. I mean, machine learning used to prepare your data, and sometimes machine learning used to analyze the data that comes out of the quantum system. So you have already a high hybridization of the way you develop a software or a solution to solve a problem. And quantum computing is just adding a little bit more of complexity in that hybridization. But this hybridization existed before, I would say. It's just a bit more complex. And one of the things that most large companies are saying, let's say the HP, IBMs, or Eviden, which is a French company in that world, they say that quantum computing is becoming an accelerator of classical computing. So you still need to know classical computing. Use the quantum computer as a kind of add-on, like a GPU. It's a bit like people had to learn how to use an NVIDIA GPU at some point, using a library like PyTorch if they do deep learning computing. So you have new layers, new libraries, probably a lot of templatization and software patterns that are going to be enabling people to solve problems in an easy way. It's about architecturing, the architecture of the solution more than just coding per se. But then your question is very relevant with regards to another topic, which is software engineering. Because software engineering is going to be highly affected by quantum computing. You need to reinvent everything. How do you debug a program when you can't emulate it because you have too many qubits? How do you certify that the program you run yields the right output? How do you make sure that you secure the connectivity between you as a client, your customer, and the computer that's elsewhere in the cloud? How do you make sure that the computer in the cloud is the one you ask to do some stuff that does it? So there are many new, I'd say, new challenges, and there's an emerging field of quantum software engineering that is popping up right now, and it goes way beyond just coding Qiskit or coding quantum gates.
Well, I have another question, which I would like to direct this to Wei, who has spent his life in computer science departments. For the preparation of this set of lectures and forums, I have looked at many computer science departments, specifically in the United States. Other countries, I have looked at those from Taiwan, and maybe Qingrui can say a little bit more about that. I have noticed that most computer science departments now are gigantic, huge number of people. I think the alma mater of Wei Zhao, University of Massachusetts, certainly has 70 or 80 faculty members in the department. And I made an effort in look at each and every faculty, saying what sort of research area they are engaged in. And I find that they are typically in the standard type of research areas, what computer science used to do. And I find almost without exception that there are very few, if any, quantum computing people doing research in computer science departments. Is this a challenge for computer science departments? Or is that telling me something else? Wei?
Your observation certainly is correct, not only true in US, perhaps also in Asia. I would say the answer may have many different ways to answer your question. I hate to say this. One is in computing field or in classical compute field, until now, the life has been terribly easy. We make a lot of money. We make a lot of easy money. Therefore, people probably getting lazy, would not want to go to very theoretical thinking. If you hear what Oliver is telling you, right? Actually, I'm glad both of us were talking. I talk much more from negative point of view, say we have a trouble here. He's telling you the trouble can be solved if you understand all this math and physics, which I agree. The trouble is my friends, my students in computer science, they have not used to that kind of math and physics. Therefore, they kind of are refusing because again, there's no demand for that, right? So far, they're getting good jobs, and they don't have to learn linear algebra. They can get good jobs. I think you probably agree with me. To learn computing, basically you can self-taught. I mean, you thank God, right? The high-level language, you literally can self-taught the high-level language. Literally any high school students without even calculus or general physics can be a really good programmer. We have many of those kind of examples.
Yeah, we have lots of examples of that.
Right. So I think that's the problem of my profession. So what I think Oliver and I both were saying is we had to retrain the people to think in the quantum computing way. What I'm saying is seems to be terribly hard, even harder for me. And Oliver is also saying, regardless hard or not, you have to do it. Otherwise, you are not able to master quantum computing. Oliver, I'm right? So basically, both of us are saying the same message from different way. He's saying, if you want to use quantum computer, you have to learn all these things. Yeah. And for computer science, I can tell you, every professor says, sorry, I'm busy on many other things. I have funding, I have money. I don't bother.
Olivia?
So I would like,
Oh, go ahead, Jim.
thank you. My last question went to Wei, so this question goes to Olivier. Thank you again for that wonderful presentation. The thing that I mean, in some sense, I kind of view your presentation as being rather pessimistic on the timescales. So I'm going to put you on the spot here. It's a question that, it's not a question that has a right or wrong answer. How long do you think it's going to take to solve the groups of problems that you outline for us to reach effective use of quantum computers? How is it going to be tens of years, or what? Do you have any estimate?
The best answer is I have no idea, but then I can elaborate a little bit.
Of course.
It depends how do you define quantum utility and for what purpose. If you look at the stuff that you can do right now with analog quantum systems or even with IBM systems, the latest ones like the Heron and 156 qubit, you can start to do interesting things in, I would say, condensed matter physics simulation, some algorithms that can be useful in physics mostly, but mostly for fundamental research and not to a real quantum advantage stage, but still you can start to do interesting things. But then if you look at the actual needs from the industry in chemistry, in drug design, in optimizations, in financial services, or in transportation or logistics, and you look at the algorithms that are already designed to solve these problems, and then you look at the benchmarks which were commissioned recently by the DARPA in the US, and you look at the resource estimates based on the chart I did show you, then you land into a zone where you need thousands of logical qubits, which means at least, given depending on the technology, hundreds of thousands of physical qubits, which is several orders of magnitude larger than the existing systems we have right now. And that's why most serious people say, we're going to wait at least a decade, if not more, because it's complicated. So you see, the answer is not just yes, no, this date, that date. It depends what you want to do. So if you want to do actual stuff that solves problems for the industry, you probably will have to wait a long time. If you want to do simple things in test beds for, I would say, simple quantum physics, I don't mean condensed matter physics is simple physics, because it would hurt some people, but it happens that condensed matter physics is simpler than chemistry. Because chemistry, these are open systems, there are many interactions, we have a lot of orbitals in molecular systems. It's way more complicated to simulate. That's why Richard Feynman said you need a quantum system to simulate a quantum system. So it's a matter of definition. What do you need? So my perspective is the best value, and there was a bias in my presentation, is that I learned a lot about that. The best value will come out of quantum chemistry, because that's where you will have a lot of business value for many industries like pharmaceuticals and chemistry, energies, whatever, climate change, stuff like that. And where I am actually very pessimistic is for the ability of quantum computers to solve decision and combinatorial problems. Because most of the known algorithms like Grover, they don't scale well, because they only bring a quadratic or polynomial speedup. And this speedup doesn't deliver because the gate speed is too slow with those systems. And as far as we know, as of today, there are very few algorithms that can solve those problems efficiently, even with a quantum computer from the future. So it shows that if there was some interesting innovation to create in the computer science side, it would be how can we design algorithms, particularly algorithms which are using heuristics to solve these problems, which could be efficient on quantum computers instead of being just providing some, I would say, minor speedups that doesn't work well at the scale of the problems we want to solve.
Merci, monsieur.
Max, do you have a question?
I do. Well, I do. So right now I am doing sort of my PhD study in education at the Harvard Graduate School of Education. And I guess from the lens of education, right, if you're thinking about scaffolding next generation of computer scientists to think about quantum, scaffolding next generation of quantum physics to think about computer, I mean, both fields are quite challenging already, let's say for undergrad. How would you design the sequence of instruction? Where do you think will be a starting point so that they are, as Wei suggested, they can be more open-minded from the get-go before they lost in the, golden handcuff of programming jobs using super high-level languages?
Was it for me or for
It's
Zhao?
for both of you.
Okay. Zhao, maybe you want to start? I don't know.
No, you go ahead.
Okay. When I look at the way quantum computing is being taught in schools, I don't know any two teachers would do it the same way. It's so funny. But
Is that a problem or is that an opportunity?
Both ways. It shows, as we mentioned before, that we are in the early stage of this industry. It shows that there are a lot of, it's difficult to teach that. Let me give you just an example of one thing that I feel is very difficult. Let's say you learn programming classically. You learn PHP or Java, whatever. When you learn this and you want to know what's in the computer at some stage of your program, what you do, you look at the variables, you look at their values, and you understand where you are. But now let's say you are in the middle of a quantum program with 2,000 logical qubits. You've got a huge matrix of 2 power a couple thousands square. How do you look at this? So how do you get an idea of what's in the data? It's very hard. So visualizing the data is one of the hardest thing to learn in quantum computing. But hopefully there are ways to understand that. You can use graphical tools like Quark, which I love, developed by Craig Guinea from Google right now. It's a graphical tool which you can use to look at the data on an emulator. It's not a quantum computer, it's an emulator. It shows you the data, so the vector state, the density matrix, and stuff like that. It's very useful because you understand what's happening in your data. But then if you develop a large code, you won't see what's inside. You will just see the result in the end. Then how do you debug a program? Let's say you have a mistake. You have added one extra Adamar gate somewhere. How do you find that? So that's why I was talking about software engineering. Software engineering will have to be entirely reinvented because of those phenomena. See what I mean? So, and you need innovation. You need different perspective. So what I feel is great when teaching is using analogies. So one analogy I use, but it doesn't work with everybody, is analog electronics, because analog electronics, some people know about that. People who know about music, for example. People who know about music, they know what's a wave. They know that two notes makes an harmonic, and you listen, you understand that with your brain. And with that, you can use analogies to explain what's superposition, for example. There are many ways to use analogies in various fields to explain what's happening in your code. You see, but some teachers, they start with just code. So they start to do gates, they show the math, and then they show the results. And then you learn how to develop a small Grover algorithm or whatever. You do this amplitude amplification stuff and equivalent. But at some point, if you want to do quantum chemistry, I'm coming back to my passion right now, then it's more complicated because you need to know classical quantum chemistry. You need to know about Schrödinger's equation. You have to know what's an Hamiltonian. You know how to simplify an Hamiltonian and stuff like that. That's way more complicated. So it depends what you do. But I would say it's about the same in classical computing. There's a big difference between somebody who develops a website, which probably knows only the rule of third in mathematics field, and a quant in finance who's developing very complicated Monte Carlo simulations and with linear algebra or partial differential equations. So this discrepancy you have in classical computing, you will find it as well in quantum computing, but it's a bit shifted towards more complexity, probably waiting for simpler tools or simpler metaphors that you could use to learn that.
Wei, do you have anything to add to that, or contradicting that?
Well, as I said, I think just different ways to express our opinion. Edward keeps saying we need those tools, which I agree. Only thing I like to say is we need to be a little bit more cautious. Or they want me to open my video. Okay, hold on a second. All right. Oh, okay. You see my beautiful face now. As I said in my presentation and also in previously answered the question, computer science is very interesting. To manage that machine and to do so-called translations, management, etc., we all have had beautiful theory behind it. Even for operating system, which is the manager of the computing system, it's not a simple engineering effort. Every part of operating system, actually, you can find very thorough theory behind it. For quantum computer, I do not know why, as Professor Feng already asked, we have not seen that kind of theory being developed. I saw, for example, the translation theory, which is the formal language, was developed in 1950s. And the operating system, all kinds of theories, more or less developed in 1960s or early 70s. That's it. Everything we used actually based on those 3 decades. Yeah, we are in the early 50s. Maybe we need to wait for something to come. But so far, I have not seen any good sign of that. That's actually the reason I'm preparing this talk. I want to wake computer science community up. So you guys do something.
Thank you. Ching-Rui hasn't raised any question or shared anything yet. Should we invite Ching-Rui to? Yeah.
Okay. I think the current situation remind me when I was PhD graduate student. at that time, the supercomputer just came out, and we start to use that. And actually, at that time, nobody really believed we can use the supercomputer to solve the problem like today, the density functional theory. We use the constant theory, try to start to do something to solve the condensed matter problem, but turned out to be very, very difficult. Or the micromagnetics maybe, but right nowadays, everybody use that. So we need a lot of people to how to say that, to invest it and devote it into that, including the computer science people, physicists, and all the curriculum people. Then, we need to wait for a while until the hardware become more mature. Actually, for Cray XMP48 came out, I'm the user. It's very hard to use that. Even the interface is very difficult to use that. But after a while, a lot of people, improve the interface, so the user become more easy to use. The interface become very friendly. I think nowadays, actually, a lot of big companies try to do that, including the IBM. The Qiskit actually right now is 1.3. So it's become more friendly to use. Also, the CUDA-Q. If you try to use the CUDA-Q and the and also the Qiskit, it will be realized it's already much, much friendly than 2 or 3 years ago. And I believe actually after 2 or 3 years, it become more friendly and the environment will become more friendly and mature. Then things will certainly change. So right now is a good timing actually to do the education for the interdisciplinary education. And I think everybody try to do that right now. Yeah, that's my comment actually for the progress.
There's another progress that we don't discuss much about usually is quantum computing is creating some pressure on classical computing to some extent. And this is a virtuous cycle because it pushes to the limits what can be done in classical computing. So, for example, when you look at the quantum supremacy from Google and stuff like that, there were a lot of progress that were showing that there was improvement in classical computing, particularly with the so-called tensor networks. So let's say matrix handling with classical computing. And there were a lot of progress there. So nowadays, people can do better chemistry on classical computing, thanks to the progress that was driven by the computation coming from the potential advent of quantum computers. And the big difference between what Qing says about the history and particularly the advent of supercomputers is quantum computers, they are competing with legacy systems which are still making progress in parallel, like NVIDIA GPUs and stuff like that. So this competition looks different than what we had in the past, even though in the past we had competition between different classical systems. But it's still interesting to see that competition showing up. And at some point, we may have some surprises. We may have also surprises coming from different fields, like what I call unconventional computing, which is in between quantum and classical, using photons or different kinds of systems, like MEM compute in the US. There are many, many companies trying different models, different systems. But coming back on a previous comment, I would say an interesting signal that this quantum computing world is very different from classical computing is the response you can give to somebody who asks you to port an existing code, classical code, to a quantum computer. What's our response usually is maybe not. It's very hard to port an existing code. I mean, let's say you've got a complicated superconducting code and you want to port it on a Qiskit. I don't know any way to do that right now because it's so different conceptually that it's very difficult to do some port. So it shows that these are very adjacent worlds, I would say. But maybe it's going to change. I don't know. Maybe somebody will invent some ways to port some vector-based classical computing onto qubit gate-based systems. I don't know.
Well, we're pretty close to our 90 minutes limit. I'm going to pose a last question to everyone. And that is, I remember I had a fellow graduate student in graduate school in physics. He was an experimentalist. And one day he had been working day and night in the laboratory. So I asked him, what is he doing? He said, well, I have this problem that I need to solve. And there are no equipment that I know of that can solve it. So my job was to design such an equipment. And he spent days and nights in designing such. In other words, necessity is the best invention. So the question is, what was the driving force for anyone, including computer scientists or physicists or anyone, wanting to come up with a quantum computer to do something that obviously classical computer cannot do? Am I right or wrong? Or they just want to do something so you can throw the word quantum into it and sound sexy? Wei, start with you.
Yeah, well, as I mentioned in my example, 1995, this professor in MIT, he came out with quantum algorithm
Who's
showed
that professor?
Sure.
Oh, sure. Okay, it is sure.
I think he should get Nobel Prize both in physics and Turing Award in computer science. Anyway, so he actually designed the algorithm and showed that the integer factorization problem, which actually is very critical in encryption industry, can be solved in polynomial time. This answers your question. This is the driving force for everybody in the world want to look into quantum computing and hopefully to utilize its potential. Sadly, yes, let me compare. Say the Turing came out, so-called Turing machine concept, right around World War II. And about 30 years later, you actually have computer used widely. I compare with the quantum computer today, right? Regardless of what happened. Bad news is in quantum computing, the progress in this early stage compared with the classical computing has been really, really slow. That drives me to think why. My conclusion is just ordinary human being cannot think computing in complex matrix multiplication. And you're right. If you learn algebra, you learn probability theory, you know, quantum physics, yes. Eventually, you can train yourself to do that. You guys in physics, I feel fortunate I didn't go to graduate school in physics. You guys in physics, for me, it was a genius. You can do all this. Even I myself, I found it very challenging to do that. That probably is wouldn't, as I said, classical computing can be done by high school kids. And
Yes.
now that's the trouble. High school kids, you teach them quantum physics. I think that's challenge.
That's impossible.
Well, you have to do it. Someday you probably have to do it.
Unless you're Julian Schwinger.
Well, hard to say. If you think 500 years ago, we don't even have a Newton physics.
That's right.
I think a human at that time, the knowledge probably is very simple. And eventually we had to thank, you know, the Newton and Leibniz, right? You create calculus, you create physics. And now at least I would say an ordinary IQ guy can learn Newton physics, can learn calculus. Now just a human now in another stage of intellectual capability, have to learn quantum physics. So I think that's actually, as I said, I agree with Oliver. He gave you a manual. Too bad. Oliver, I think the challenge for you is, can you simplify the menu so the high school student can swallow it? For me, that's tough.
You can make a parallel with the AI. If you look at ChatGPT and transformers, it's hard to understand how it works. It's hard to develop your own, but you can use ChatGPT because it's an end user tool. And you can even develop your own AI based on those tools using the APIs that are available. So I'd say that to some extent, it may happen like this in quantum computing world at some point. But let's go back to history. Before Shor in 94, there was Richard Feynman in 81, 82. And his idea was to use a quantum system to simulate other quantum systems, and that led to the creation of more analog quantum computers and then gate-based quantum computers. So the two tracks are, one is cryptanalysis, but I would say it's a dark side of computing because it's breaking the internet. I don't see much value in doing that, at least a positive value. And then there's a bright side, which is do physics simulation, chemistry simulation, develop new stuff, solve complicated human problems. That has a very positive stance. But this is complicated. But it's already complicated even if you do classical quantum physics using a classical quantum system. So that's the same. But then you got a chicken and egg problem. The chicken and egg problem is you can't do everything we described because the systems are not there yet. So there are people working very hard to build those systems. When those systems are available, there's going to be a big question about their price, the energy consumption, the computing times. And if those three factors are in the acceptability range, you will see people learn that, probably not in high school, more at PhD level, but you will see more people learning that because there's going to be some utility. But as in AI, you will have a difference between those people who use it and those people who develop the tools. It's the same in many places in IT, I would say.
Well, we're coming up to the 90-minute level. Jim, do you want to make some comments here?
Yes, thank you very much, Hsuan. First of all, I want to thank our guests for giving an extraordinarily transparent and deeply informed discussion for the folks who have joined us. I know this has added to my understanding to the complexity of the problem. And it also, I think, should be a message to especially folks in the quantum computing and quantum science world to alert them of the magnitude of the challenges. In physics, we've seen these things before. In my part of physics, we see it all the time where there's what is purported to be a fundamental breakthrough. There is a period where a large number of people rush into the area, and then it doesn't quite live up to the expectations. And so that's actually my deepest worry about quantum computing, is the rate of progress going to be sufficient so that the buzz around the area and therefore the support that comes to the area will be enough to drive it to the potential that we all hope it reaches.
Jinrei? You need to unmute.
Yeah, I think I agree, both Professor Zhao and Oliver just mentioned. Actually, probably still need a certain time, but I think the driving force for most people comes from the economic reason, because actually we believe actually quantum computing can solve the non-polynomial problem and the NP hard problem. If that was really done, in certain killing application, it will make a lot of profit, actually, no matter in which part. But we need certain time to prove that. And together, the first killing application, then things will suddenly change.
Well, I think that the human mind, despite all the words nowadays called artificial intelligence being thrown around all the time, human intelligence is still the most important thing. I remember having a conversation with a field medalist from France, He was supposedly one of the youngest fuse medalists many years ago. And we were discussing who would be the first person to take square root of -1 very seriously. You know, think about if we did not take square root of -1 very seriously, we wouldn't have any. We started our discussion in Wei Zhao about complex numbers. And if we don't take, you know, think of square root of -1, how stupid can that be? And yet, if there's no square root of -1, there would be no quantum mechanics. And there would be no internet, there would be no cell phone, there would literally wouldn't be anything. There wouldn't be electromagnetic theory. So I think that we should give confidence to the human mind, who is always able to ask the most difficult and most ridiculous question and turn it into something exciting. I don't know whether quantum computing is in that direction or at that level. But to put quantum into classical computing, clearly to me, means that human beings are seeing something that 99.9% of the population in the world don't see it yet. And as physicists, as computer scientists, we're both defined as scientists, but multidisciplinary scientists. We should really work together. And we should see more physics department talk about quantum computing. And we should see more computer science department talk about quantum computing. The language may be different, the languages may be different, but the aim should be aiming in the same direction. And also find a problem that cannot possibly be solved by the classical computer and which we think can be solved by the quantum computer. And anyway, again, I agree completely with Jim. Our two speakers today, Wei and Olivier, they have gone several orders of magnitude above what I have expected that they would say. And perhaps what we can do, Jim, let's think about it, and maybe ask each of them to give a full discussion of theirs in the future, in one of our future talks, if they don't mind, so that they're not constrained by the time today in their presentations. Anyway, thank you all. Jim, any last comment? You're muted.
No, Dr. Hsuan, I don't have anything to add. You have given us our benediction.
Oh, okay. All right, everybody.
you.
Max?
No, thank you. This is
Okay.
such a great session. Thank you so much.
Okay. Good night, good morning, good afternoon.
Bye.
Bye-bye, everyone.